we discussed product topology. What is that product topology? Just to recall, let X be a set, B be a subset of power set of X. That means subsets of, set of subsets, some set of subsets with the property that number one property is that union of all U belongs to B, U is equals to full space X. Second is that if U1 UR is belongs to this B, and then for any X belongs to intersection of this UI I equals to 1 to R, there exists a set B belongs to this B or capital W such that X belongs to this W, and which is contained in the intersection of all U equals to I to 1R. Now let tau be a collection of subsets of X, collection of subsets X with the property U subset of X with the property, what is the property? Subset of X with the property what is the property that property if X belongs to W, there exists B a WX in B such that X belongs to this WX which is contained in U, then tau will form a topology that we have discussed last day, called topology generated by this B, and B is called basis of the topology. B will be basis if it satisfies. This is the basis property that for every X belongs to, for every U there exists. That B will be basis if for every U belongs to the topology there exists an element containing that X, such that B is said to be basis of a topology tau if for every element U belongs to tau and X belongs to U, there should exist an element WX from basis such that X belongs to WX subset of U. Okay, if you have not understood anything I am talking or I'm just writing, then you can just directly message here, or specifically if it will be better if you open your mic and speak it out, and or there is any doubt regarding the weekly lectures uploaded from NPTEL, you can ask here. We will obviously discuss those things. Okay, then this is called topology. Now this was the just recalling. Let X be a topology, X with Tx be a topological space, and Y Ty are two topological space, then if I take this B is equals to this U subset of V such that U coming from the set tau X, U coming from tau X, and V coming from this tau Y, then this beta will satisfy this particular two properties. Okay, particular two properties mentioned just few, these particular two properties. Okay, so beta will satisfy this particular, then beta, this is I will write that property, then beta will satisfies properties mentioned above. Okay, then the topology generated by generated by beta is called product topology. And one more fact is that, for example, if I take R, it will have an topology, standard topology. Okay. Now, if I take this is as a product topology, now if I now what I'm saying, okay, this will be there. This is not aimed actually. So I have to write. This is called product topology on X cross Y. Okay. Now, if now if I take R square, okay, then it should have standard topology, and I also get the topology on R square as the product of the topology tau of R cross this one. As a product, I also get the topology on R square. Also, R square has a product of standard topology. Then we also last day discussed that standard topology and product topology. Standard topology and product topology of R2 square is same, and not only for R square but for any positive integer n. For any positive integer n. Okay. Now, okay. Now, let now one problem first I will try to discuss those exercise which is mentioned in sir's note, lecture note. Those I will try to discuss. In lecture 6, in third page, there was a example. Here is a little exercise is there. Define, this is, I can write a little exercise. I can just, this is define just a minute. Okay. Let what is called that define a topology. Define topology on the space of complex number. Topology on C. This C is the space of complex number. How? U is subset of C, which which satisfies the following property. We have seen this last day also. Following property. What is following property? That if Z is there, Z is for all Z belongs to this U, there exists an epsilon greater than 0 such that this B epsilon of Z, which is equals to mod of all those Y belongs to complex number, all those Y coming from complex number, such that mod of Y minus Z is less than epsilon. Okay, this is just something like a unit ball radius epsilon centered at Z in the in C. Okay. Then C has a topological C has a topology. Then C will form a topology with this um, define topology on C. U belongs to U subset of C. Topology tau one. I will write this one as a tau one. Topology tau one on C. U belongs to U subset of C is in topology tau one if it is satisfy if it satisfies satisfies following property. Okay, this is the property. Now if I take phi is a map from R square to complex number defined by defined by defined by phi of x comma y is equals to x plus iy. This is just a map. I am not writing anything. Okay, then as C has a topology, C has topology. Obviously, C has a topology. Now we know R2 have a standard topology. R2 has standard topology. R2 has standard topology. Now if I take the collection of all subsets like P of U such that U belongs to the standard topology of R2. R2. Then first task, then tau 2 will form a topology. Tau 2 will form a topology. Why this will form a topology? Now let's check. Indeed, let's check why it will form a topology. What is the three property? That first property is that obviously you can say that and empty set and R square is in the topology, standard topology of R square. Then then their image under P P of empty set, then P of empty set is again empty, and phi of this R square, that will be full C. Okay, so that implies empty set and C is in the tau 2. So I want to say that this tau 2 will form a topology on C. So first condition is that empty set and C should be there. So these two are there then. Second condition is that arbitrary union. Let u1 u2 dot u, sorry, ui, not ui. Let ui belongs to tau 2 for all I belongs to some indexing set I. Okay, then I want to show arbitrary union is there. Then as ui is there, so there will be some vi, like let ui is there, then there exists vi belongs to standard topology of R square, standard topology of R square, such that f of vi is equals to ui, because set is something like, sorry, phi of vi, not f of vi. Phi of vi is equals to ui. Then you can see this, now vi belongs to standard topology of R square for all I belongs to capital I. That implies union of all I is coming from I, which also belongs to the standard topology of R square. That implies that phi of union of I belongs to capital I vi, which is equals to union of I belongs to capital I phi of vi, which is equals to union of I belongs to capital I ui, that is also belongs to tau 2. So arbitrary union is arbitrary union of elements, arbitrary union of, sir, could you explain the second point again? Yeah, sure. Arbitrary elements, just letters, arbitrary union of elements of tau 2 is again in tau 2. Second point means, okay, let ui are elements in tau 2. What I need to show that arbitrary union of and corresponding to, for I mean basically for every I belongs to capital I, ui belongs to tau 2. Okay, now what I want to say, so that arbitrary union of this ui is again in tau 2. That means I have to show that union of all these ui I is coming from I2 is an element of tau 2, right? I have to show this. Now, what is the collection of tau 2? That is that phi of u is coming from standard topology of R. That means there exists some open set. There are actually open set in R square. Vi belongs to standard topology of R, such that if phi of vi is equals to ui for all I belongs to capital I. Okay, now this vi is in standard topology of R square. Okay, this vi is in standard topology of R square. Is there any problem with my screen? I mean, is it clear now that whatever I am writing? If it paused, then you can message. Still, I'll try to fix that one. Okay. This Vi is in. How do we know that V is in open? That is the collection. That is the collection. How tau 2 is taken? U is in the standard topology of R square. So elements, every elements in tau 2 is something like phi of U for some U in the standard topology of R square. Is it clear? Or should I repeat once? I am saying, if every element is something like that is something like phi of some open set element. Okay, so that way this Vi will be something like, sorry, Ui will be something like phi of Vi. Now Vi is an element of standard topology of R square. Now as that is standard topology, so arbitrary union will also be in R square. Now arbitrary union is in R square means this phi of arbitrary union, that is this thing is clear. I think there is no problem, I hope. Okay. So this phi of union of Vi is equals to union of I belongs to capital I, phi of Vi, which is equals to union of I. So this is, as this particular thing is in R square. So phi of that is that this thing is belongs to tau 2, tau t. This will belongs to tau t. Sorry, I'm just spelling it. Tau of 2, tau 2. So so arbitrary union of elements of tau t is again in tau t. Tau 2. So that, so arbitrary union is there. Now last point is that finite intersection. Finite intersection will also be there. Let, that is similar way. Let U1, U2, UR belongs to standard topology of belongs to that tau 2. Then there exists open set or elements in standard topology. Open set Vi belongs to Vi of R square for all r equal for all I is equals to 1 to r, such that phi of Vi is equals to Ui for all I equals to 1 to dot dot up to r. Then now as Vi is in there, Vi is in open standard topology of R square or open set, same thing, standard topology of R square. Then intersection of Vi is again in the standard topology of R square. That implies phi of intersection of Vi, I equals to 1 to R, I equals to 1 to R, is again in the standard topology. No, not in the standard. By definition, this will be in tau of 2. But note that phi of intersection of I equals to 1 to R Vi, that will be same with the phi of Vi I equals to 1 to R, which is equals to intersection of I equals to 1 to R Ui, and which is also belongs to tau 2, because this one is belongs to tau 2. So finite intersection of elements, so finite intersection of elements is again there. So tau 2 form a topology on, so tau 2 form a topology on C, topology on complex variable space. Okay, now second thing is that we will show that these two standard topology, what that we have defined a topology in C and the beginning, that that you will be in the topology, or you will open set if for every epsilon greater than 0 I will find, sorry, every epsilon greater than 0, sorry, every Z belongs to U, there exists an epsilon greater than 0. For all Z belongs to U, there exists an epsilon greater than 0, such that this will contained in the U. Yes, Abhishek.
So, if you want to define a basis
Yes.
for some Rn or any in dimension on the real line,
Hmm. Hmm.
so the condition less than epsilon, that must be a
Hmm.
metric, right?
Uh, no, not metric. That there is a very, I mean, yeah, I just, yeah, metrics thing is something not introduced yourselves, but okay, I know that this is something metric in complex, okay, but without metric we can even give topology, right?
But it may not be standard.
Yeah, it may not be standard. Obviously, it may not be standard topology.
But if
Yeah,
you want to say the standard topology, then it must be a metric. Is it? Am I correct?
mm, I mean, and how you first say a metric, that is the first problem. Suppose you have a collection of open set, and you know what is open set means, like something like this way,
No, just
right?
in the basis, when you want to find the distance. So if the
Yeah.
distance is not a metric, then that's gonna be a
No,
problem to
distance
define
is
the
always
neighborhood,
a
right?
metric. Yeah, yeah, understand. I mean,
Yes,
your
yes.
thing is something going to be true in some little earlier, but right now, if you suppose that you have a we have defined a standard topology, right? But to define standard topology, we have used the distance concept, right? This is distance concept.
Yes, yes.
So without distance concept, is there is not, and metric is nothing but distance concept. Okay. I hope your this thing is correct. That suppose, I mean, basically what your questions will be, that suppose I am taking r to the power n, I am taking standard topology on them. Okay, whether that standard topology is coming from the usual metric or not. I mean, for a metric space, there always a stat topology. So question will be like whether standard topology is always coming from the that metric or not. Okay, I hope this is the thing. I mean, standard topology or standard topology, whatever standard topology we are saying, that will be coming from the metric. Okay, I mean that topology will be metrizable, and uh, that metric will be the whatever distance is something. Yeah, okay. So your question will be more generally that whether standard topology on R to the power n is metrizable or not, whether that is coming from a metric or not. I think that is correct. That is yes. I mean that needs some little work, but that will be some little advance. But that is correct, I think. If I'm not, I'll try to check once again. But it seems to me correct. I'll obviously clear your doubt. But I mean correctly, I will say the next. But it seems to me that there obviously it should be metrizable. Clear?
Yes, sir. Yes, sir.
Okay. Now we will show so that there is two topology. What is that? First topology is that let u a subset will be in the topology tau one if for every z belongs to u there exists an epsilon greater than 0 such that this element should contain in u. And secondly is that we have given a map phi from R2 to C by this way, and then we have given a topology on C. Now we will show that these two topology are same. Okay, we will show that tau 1 is equals to tau 2. Okay. Now how we will show that? If I can say any element of tau 1 is an element in tau 2, then we are done. I mean, like similar way, let u belongs to tau 1 be an element. Then by definition there exists then by definition for epsilon greater than for every epsilon greater than for every x belongs to z belongs to that z belongs to u, there exists an epsilon greater than 0 such that mod of such that this particular b epsilon fz that is equals to those whatever symbol I have used there y, those y belongs to complex such that mod of z minus y less than epsilon, this should contain in u. That is the definition. But now I have to show that this particular set actually image of this particular set u, actually I have to show that that is contained in tau 2, right? So that particular set is contained in, then show the tau and tau are same. Huh? That particular topology that I have to show that this particular thing is actually image of some element, some open set in standard topology, right? And that is, now we can say that from here we can say that this U is particularly B epsilon of Z, union of all Z belongs to U. I can write this one. Okay, for all Z belongs to, okay, I will just, how this is working, I'll write the if that 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 okay, that will depend on Z. So what I'm saying is that U is particularly union of all Z belongs to U B epsilon depending on Z, center at Z. This way, how how I'm saying that? Note, for every z belongs to u, there exists an epsilon greater than 0 such that b epsilon z is some subset of u, and z belongs to there. Now, for now that seems that for every z belongs to there, that means u that means that u is particularly collection of all z belongs to u, and that is contained in, for every z belongs to, that is contained in union of b epsilon z of z is coming from u, and that is also subset of u. So from here we can say that u is equals to union of z belongs to u, b epsilon z. This epsilon z means nothing but epsilon depending on z. Okay, so I can write this one. So I'll erase this one because this is uh, just for rough. I'm just saying. So now this b epsilon 2z, those are, what are that? That is that y belongs to c such that z minus y is less than epsilon z, right? That means this y is something like y1 plus iy2 such that this z is something like z1 plus iz2. That means some summation of root under z1 minus y1 square plus this mod is, sorry, plus root under z2 minus y2 square. This is less than epsilon z. Okay, but this particular set, then if I take corresponding particular set, uh, just a different symbol, the w epsilon z, something like all those y1 comma y2 coming from the set R2 such that root under z1 minus y1 square plus z2 minus y2 square is less than epsilon. Let z, I am taking z1. I'm not writing x1 plus x2 right now, just z1 plus iz. These two are real. Okay, that z1, z2 are real. Z is, I know that z in general denoted by complex what I have written. So okay, I can wz. Now wz means this will be like w corresponding to z1 comma z2. This is contained in the standard topology of R. Standard topology of R square. And this phi is actually w epsilon of z1 comma z2. This image is actually this b epsilon z, right? So what I can say is that this u is particularly union of all z belongs to u, b epsilon z of z, which is equals to union of z belongs to u, phi of w epsilon z1 z2, this one. So this will be like phi of union of z belongs to a set, z belongs to a set u prime. I am writing what u prime. I am writing that w epsilon z1 z2, where u prime is equals to all those z1 z2 belongs to R2 such that z1 plus iz2 is belongs to u. Okay, then note that now this is arbitrary union. Okay, these are open set actually. These are open set. No, sorry. I need to say that. Okay, now note that this w epsilon z1 z2 are open set in standard topology of R square. That implies this union z belongs to this u prime, not z belongs to, this will be like z1 comma z2. W epsilon z1 comma z2, that also belongs to the standard topology of R square. Okay, So that means phi of this image actually is in tau 2, which is actually phi of this image actually basically our u. So this is in tau 2. So what I will say that tau 1 is subset of tau 2, that we have proved. Conversely, we have to use the same technique. Conversely, if if some element v is in tau 2, okay, that means v is in that means v will satisfy the open set property. Converse will hold similarly. That I think that will go similarly. There is no problem. I think. Should I say prove converse, or converse is clear from here? I mean, if I need to prove converse, then please say. Otherwise, I'm just writing converse. Similarly, we can prove the converse. Just do I need to prove converse, or is it how to subset of Taiwan? Okay, I think I am not proving them now. Okay. Okay. Next thing is that continuous map definition. Okay, we will start now. Continuous function. Continuous map between a topological space. Let x tau x and y tau y are two topological space, are two topological space. Phi is a map. F is a map. There is no not phi. If from x to y is called continuous. This is very important thing. Continuous. If for every open set V belongs to tau y, F inverse V is again in tau of x. That means inverse image of every open set is open. That means inverse image of every open set is open. Whoever, I mean, studied that real analysis course, then their continuity. So there is also the continuity definition is same, but their open is something little definition is different, but actually same there. Nothing special. But here we are defining in general topological space. There obviously the topological space is fixed, that is R, real analysis case. Okay. Now, what is the example of these continuous functions? Examples of continuous function. First one is that let x tau x be a topological space. Continuous function definition is clear, na? If there is any doubt, you can just ask me if there is any doubt. Okay. Otherwise, I'm just going ahead. X tau be a topological space, and let y be a subset. Let y be a subset of x. Then y will have, then we will consider always, when we will consider any subset, that means where there I will consider subspace topology. Then we will, then y will have subspace topology. So what is subspace topology? We call tau of y. This tau of y is basically this y intersection of all u is coming from tau of x. This is basically okay. Subspace topology. Now define now the inclusion map this I from this y to x by I of y is equals to y is continuous. First condition is this. How this is continuous? We will prove this one. This is continuous. Let this is very clear. Just still you can prove that let u belongs to tau of x be an open set. Be an open set in x. Then what is the inverse of this u? Inverse of this u is basically the same thing. Inverse of this u is basically that y intersection of u, and which is always contained in tau of y by definition. So inverse image of open set is open here. Then inclusion map, this is called inclusion map. Inclusion map is continuous. Okay. Second example that I will go to product topology. Okay, but before going to product topology, here I want to say something. Note that here whatever that x tau x is in topological space, right? And y is in subset. Then y have the subspace topology, but y can have any other topology, right? But here what I will say, the smallest topology on y for which the inclusion map. Now what I want to say basically is that I just want to make some rough thing. Here I'll just write remark here. Remark here. Let x is in set, y is in subset of x. Then this map from y to x can be defined always, right? Y equals to y. This map is defined always. Suppose x has a topology, x has collection of open set. Now we have showed that y with the subspace topology coming from tau x. If I take y with subspace topology coming from tau x, then this a particular I is an I is continuous function. That is inclusion map is continuous function, right? But what I want to say is that now here I just want to just go some backward, that let y be in topological space, y be a set, and tau 1 tau 2 are two different topology. Okay, on y. Then we say tau 1 containing tau 2, if every open set in tau 1, tau 1 is actually particularly a collection of sets, right? And tau 2 is also collection of sets. Tau 1 subset of tau 2 means every open set in y tau 1 is again an open set in y tau 2. But a open set in y tau 2 did not be an open set in y tau 1. So this is means that tau 1 is contained tau 2. Okay. Now I will use this concept. What my remark is that claim, I'll just write that subspace topology on y is the smallest topology, is the smallest topology for which inclusion map from y to x is continuous. Okay, what means this smallest topology, all those things? Because what I'm saying that we can define, if y is subset of x, we can define y from x to y, I from y to x. Now x has a topology tau x. Now if I give y with the subspace topology of x, then y, then this map is continuous. But right now I am assuming that in y I will not give the subspace topology. I will consider another topology. Okay, another topology like some different topology like tau 1. I will give tau 1 that topology. Now this function, then this function will be continuous or not. That depends on this tau 1 and tau x. Okay, we have discussed first that this inclusion map is actually continuous, but here topology is that x has topology and y has subspace topology. But if I give another topology to y here, then this map I need not be continuous function. Okay, need not be continuous function. For example, what I will say, I just want to give a non-continuous function. Let f is a function from R to R, and give f of x is equals to R is a subset. Okay, this is inclusion function. Okay, inclusion. Okay, that I have to check that whether always inclusion function is continuous or not. But problem is that this continuity is very much property of topology. Okay, this is not the property of set. This is property of topology on that set. Okay, so now still suppose tau one is a topology for which I also again and I again continuous function. Then what the claim is, this remark is saying is that then the collects this tau one will contain the subspace topology of y. Tau one is the smallest topology. For any topology tau one, if this is the, for any topology tau one, yeah, I think that can be given. Inclusion map can be given. For example, I am taking y is a subset and x is a set, giving I is a map, give y topology, empty set and y. For example, okay, I got it. Let I is a map from R to R. Okay, just R to not R, 0 1 comma 0 1 0 close 1 to R, sending x to x. Then this is inclusion map. Now give topology 0 1 with the topology tau of 0 1, which is actually collection of the two set, empty set and 0 1, right? And but then with this topology, this inclusion and R with the standard topology, this inclusion map will not be continuous. Okay, so inclusion map is not always continuous. So that is depends on the what topology we are giving. It is sure that if I give the subspace topology, then it is continuous. But it can be continuous with other topology also. Suppose with different topology tau one, this is continuous. I is again continuous. My claim is that this tau one will contain the subspace topology. That means subspace topology is the smaller among all the topology for which I is continuous function. Okay, that I will just prove right now. Okay, what I want to say, hopefully it is clear, right? If it is not clear, please say it. I will just try to discuss, because these are very conceptual things. Okay, these are very conceptual and very important. So you should not be in doubt or it should be in confusion. Now let tau one be a topology on y, and let, yes, by smallest we mean the cardinality of the set, right? Yeah, in somehow you are correct, but in one sense you will not be. Why? Suppose a set have infinite number of subset. Two set is infinite. How can we say that how the cardinality is different? Cardinality still can be different. For example, thus this q is subset q and q and integer number or natural number. These three set has same cardinality, countable, right? But obviously this three set is not contained. This q is not contained in here or there, right? So there is an order. So cardinality means when finite, then we can say cardinality. Otherwise, subset. Subset means this topology is particularly collection of sets. Okay, topology on a set, it's actually particularly collection of sets. Just subsets of tau is subsets of px. Px is the power set. Power set is the collection of all subsets. Okay, now this tau one is subset of tau two, means whatever subset here, those subsets will be tau two. Those subsets will be tau two. But whatever subset in tau two, subset means subset of x, they may not be an element of. Whereas tau one, tau two is collection of subsets. They are again a set, but okay, they are collection of subsets. So in that sets, the inclusion of smallest means. Okay. Now here what I am saying is that I will always denote tau t or tau y is the subspace topology of y. Okay. Subspace topology. Now tau one be the again a new topology of y such that this I from y to tau one going to x to tau x is continuous function, right? Continuous function. Now what I want to show is that every open set tau y, what is the tau y? That is y intersection of all u such that u is coming from x. These are the open set. I have to show that any element of the from these is contained in tau one, and that is very much clear. You can look at this. How? Let as I is continuous, what is the definition says that continuous inverse of every open set is again an open set. Again it should be open set. I is continuous, then for any open set, whenever I will say open set u in x, that means u is actually element of tau x. That is same thing. Elements of tau topology are called open set. That is the same. So I am writing every open set u belongs to tau of x, I inverse of u, that is actually y intersection u. So as I is continuous, so this should be contained in tau 1. So that means tau of y is subset of tau 1. Is it clear? If there is any doubt, please, any doubt, any small, or you are not able to hear me, so you can ask me. Otherwise, I'm going ahead if you don't have any problem. Okay. So is it clear? I think just subspace topology is the smallest topology for which the inclusion map will be inclusion map will be clear. Okay. Thank you. Now what I will say here. Okay. These two are the example of continuous function. Okay, now I have given an example of continuous functions. Now I can give more example. That example 2, that let I am just let x1 x comma y, just to two set x comma tau x and y comma tau y are two topological space, right? Topological space. Then x cross y, then there exists a product topology that I have mentioned in early. There exists a product topology on x cross y, which is generated by this particular set B u cross v, such that u is coming from tau of x, v is coming from tau of y. Now I will define a map px, then beta will be basis. That is also clear. Then beta is basis for product topology tau x cross y on x cross y. Okay. Now what I want to clear that for x belongs to, I am just writing this px just to symbolical x, px from this x cross y to x by just I'll just input this map is always defined. How? This p of x comma y is equals to, or I can write this is capital X, this is all. Then similarly I can define p of y x cross y to y, then p of y xy is equals to y. These are called projection. These are called projections. Obviously projections according in which set, that is clear. Now p of x or y from x cross y with the product topology to x with the topology of x is continuous. How this will hold? Okay, how this will hold? I will prove one. Similarly, p of y will also be continuous. So how will say let u belongs to tau of x be an open set. Okay, then inverse of this px inverse of this u. What will be this? This will be like this will be u cross y. Okay, is it clear? Px inverse of u, because if you note at the p of x, what is map? X comma y goes to x. Now I am taking an open set u in x, right? Now what will be the inverse image? That u cross y, because every element x belongs to u, x comma y, for all element y belongs to y, this will go to the x. So whatever element in y doesn't matter. It will, if the element coming from y, then it will go to sorry, if the element is coming from u, then the image of this set will go to u. So basically inverse image is basically so basically inverse image is basically this. I hope this is clear. If there is problem, just please share, because these are These are important things. These are building blocks. If you should not be confused or should not be in doubt here. Okay. So these are this is the element, but we know what is the element of the basis, that u cross v. U is coming from tau x, v is coming from tau. Now, but u is coming from tau x, that is by definition, right? And y is always coming from tau y, because tau y is topology, so it should contain empty set and the full set. So this is contained in B, but this B is obviously the in the inside the product topology space, right? So so inverse image of U is in product topology. So projections are continuous. I hope it is clear. Okay, is it clear now? Similarly, let x1 dot dot x I can take finite product topology two way you can say. Two way we can say the product topology. One is finite, for finite number of elements the product topology. Suppose for example I am taking here finite xr with topology tau of xi, then the p of I from product of xi I equals to 1 to r going to xj. I am writing here j xj by p of j x1 x2 dot 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 xr will be xj is projection and continuous. Yeah, how image of u is present in B. Okay, that is good. Okay, if they are clear. What is the set of B? If you look at the set of B, that u cross v, u is coming from the topology of x, and v is coming from the topology of y. Now, what I need to prove? To prove that P of x is continuous, that inverse image of every open set in X is again an open set in the product topology. Let U be an open set in X tau X, right? So that means inverse image of that set is U cross Y. Now, question is why inverse image of that set is U cross Y? Because it is very much clear that how P of x is defined. P of x mapping x cross y is x only, right? So whatever inverse image of, I mean, so this basically this is just sending, I mean, what I will say here, if x is in U, then what will be the inverse image? What will be the elements for which the P of x is actually, that the elements is x comma y, x cross y, such that y is coming from capital Y. This is the element for which P of x, x comma y are equals to x. For every x belongs to y, this particular subset is the pre-image of x, because every element of this set is going to x, and this is the only element of x cross y which is going to x. Right? Clear? So you will be in the this pre-image hopefully clear, that this pre-image is clear, but 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 also note that what is B, that U cross B. So how we know Y belongs to tau? Yeah, that is by definition. What is the definition of topology? That definition of topology I just proved that one, that it will be topology that if it satisfies three conditions. I have not said the definition today, but definition is that first is that full set and empty set. These to be element of the topology. Okay. What I am saying, I just need to show that y belongs to tau y. Suppose y is set for any topology tau y on y. First condition is that set empty set and y should be in tau of y. This is the minimum definition. Whenever I am saying topology, that means these two are there. This is the least smallest topology or trivial topology. They are called trivial topology. If I take the tau of y is only collection of this set, whatever set will be, that set will contain this subset always. Whatever topology on y. Okay. So yeah. So y will always be in tau of y. If y is always in tau of y, u cross y will also be in tau of x cross y. That u equals being in basis, and basis is always contained in the topology. Now what I am saying is that this projection I have done it for two situations, but I can say for any arbitrary situation, this projection is again continuous function. Similarly, I can say, okay, I hope so. These projections are continuous for all j is equals to 1 to 1. Now, what I have not said, hopefully, Sir also said, at least said, that product topology, I have said product topology on finite number of finite product. X1, X2, XR are said, finite product I have said. Because similarly, the product topology, how defined for the 2 by 2 situation, similarly, you can define product topology for the more situation. But product topology for infinite set, product topology for infinite set, infinite product topology for product of infinite in the space of infinite product. In the space of infinite product. What basically means is that let I be an set, indexing set, just indexing, that can be finite, infinite, just some element is there, that's the only point. Maybe that can be finite, infinite. Okay, right, finite case we have done, so for right now I will assume that infinite. For every I belongs to capital I, there exists a topological space that xi comma tau of I, right? Now we will define a topology on the product of this xi. I belongs to capital I. How this product of xi can be says? This first of all on define called product topology. Okay. How this topology defined? This first of all, how this product infinite product is defined. Infinite product is something like a sequence, nothing special. Sequence can be countable, uncountable, that doesn't matter. Sequence in general it is countable, but okay. Thing is that this LE element x belongs to this product of xi. I can write this element as xi, I is coming from I. Something like this way. I can define the product elements of this product. Okay. Now what I am saying is that I will define a topology on this set, and which will call the product topology. Now let B, I will define this B set. B is equals to union of, not union, so actually product of ui. I is coming from u such that ui belongs to xi tau of tau I. Ui is the open set in xi, and the set is which is equals to all I belongs to capital I, such that ui is not is equals to tau I, ui is not is equals to xi is finite. What basically this means that, what I want to say, just I'll read once. Beta is the set that product of ui. Product of ui means like the first one, like it's finite case that u2, u1, u2, u3, like that way. But that can be infinite product. Okay, that is what. This product of ui such that ui should coming from the topology tau I. There is also we are taking that u is coming from tau x and v is coming from tau I. But here what I added is that the set is where ui is not equals to xi. Ui can be xi, right? Because xi in tau I, because that is what I think I just few minutes ago I just try to discuss that xi always in tau I. So ui can be tau I. Xi is always in tau I, so ui can be xi. Now what I'm saying is that the set where this ui is not xi, that should be finite. So basically what I am saying, we can take this element something like u1 cross u2 cross u3 cross, but something like un cross, like that way, right? But what basically this means that beta is a collection of all those this type of elements for which all but finite number of elements are xi. I mean, except finite number of elements, other will be like xi, full set. They are not a subset. Okay, is it clear? Is it clear? Okay. So that is what that all but finite. I think this term you have heard that. That means that this in this product all but finite number of will be the full set. Okay. There is very important. I mean this finite number of. If I don't use this S thing, that S is finite. That means the set where ui is not equals to x. I mean most of the cases except finite number of cases, this ui will be the full set xi. Right. That is what means. Okay, so now this beta, then the topology generated by then beta will satisfy the proposition, beta will satisfy the properties of the properties mentioned above. What property that mentioned above? What property that union of all elements u coming from beta will be the full set, this product of xi first. Second is that if I take u1, u2, ur belongs to beta, then x belongs to u1, intersection of ui I equals to 1 to r, then there exists an element wx belongs to beta such that x belongs to wx belongs to intersection of all ui I equals to 1 to r. So I am just saying that this beta will satisfy the property that is I think you will find in Sar's node or in anywhere else. But so beta will satisfy some property mentioned above, then topology generated by beta, topology generated by beta is called product topology. Product topology. Note that product topology on this product particularly. Note that when this main set I is finite set, that can be finite. I have taken I is a subset, but I can be finite, right? If this I is finite, then the product topology defined just in last and the product topology defined in above, like this finite product sense, these two are same. Okay. Then note that when I is finite, then both the product topology defined above are same. Product topology defined above are same. So whenever I will take, I mean there is basically two things. Whenever I will take finite set, then just finite number something this will happen, but there is no need of this particular thing when I'm take, because you can say, I mean just what I'm to say is that if I is finite, then this S set will always finite, na? Because S is subset of I. Okay, whenever I is finite, this S set will be finite because S is subset of finite. So product topology is same basically. But if I is not finite, but then we badly need this particular S should be finite. Okay. Now, so similarly, the projection pi I from product of this xi, I is coming from I to go I, is defined by pi of this particular xi, I is coming from I. This is the element. This is equals to, I will write j here, j. This xj is continuous for all j coming from I. Also note that here we can define a new topology. Note that, so okay, it is clear that whenever I will take infinite number of sets, then how that product topology is defined. I hope it is clear. Now here I will define a new topology on this full set, box topology. What box topology? Let I be an set. Okay, and for each I belongs to capital I, xi comma tau I are topological space. logical space. Okay. Now take beta is equals to product of ui such that ui is coming from tau I. This is all. I am not taking anything. If you note that last I have taken this one, but I have taken more. That this ui except finite number of ui, all ui will be x. But here I am not taking any such conditions. That means here ui can be infinite. For example, what I want to, okay, share, just let me complete this one, then I will discuss the dot of, then this beta set will satisfy the properties of being basis that mentioned above, that union of the same union will be there and intersection will be there. Intersection will be there, okay. Will satisfy the property of being basis. Then topology generated by beta is called box topology on this product. One remark here is that when this I is finite, box topology and product topology are same. Okay, what I have just discussed there, that suppose I have taken I is a set, that is just a set, okay. I just said finite, infinite, I'm not saying anything. Okay, first what I'm saying, that beta, if I take beta 1 is the collection of all product, like product means this product means this product of ui, I is coming from u, that means this u1 cross u2 cross like this way, but I don't know whether that is countable even. Okay, so this ui such that this ui is coming from tau I, but the set is where all those indices for which ui is not is equals to xi, this is finite. That means in this product, except finite number of elements, every ui will be the space xi, full space. That is what I mean. So this is the, and the topology, and this beta 1 will be the satisfy the property of being the topology, and the topology generated by beta 1 is called the is called the product topology. This will give the product topology, okay, product topology. And beta 2, what beta 2 means? Beta 2 means this, I'll just write this one is the rough. Beta 2 means that I am taking full product. I am not saying that whether finite or infinite can be element. This is the thing. That means here in infinite number of ui can be not x. Okay, I mean here it can be like u1 u2 cross cross, like infinite number of it is going like this way. None of ui is the set xi. None of ui is the xi. So you can see here, then this beta 2 will also satisfy the property of being the topology space, being the basis of the topology, and the topology generated by this beta 2 is called the box topology. So note that box topology. Note that whenever this set I is finite, this beta 1 beta 2 basically same, right? There is nothing to mention that whether s is finite or infinite. S can be finite or infinite, right? When I is finite, beta 1 is same as beta 2, right? Okay, this is the same thing actually, okay, whenever I is same. But what interesting fact here is that if you note that any elements in beta 1 is again contained in beta 2, but any element contained in beta 2 that may not contain in beta 1. Is it clear what I mentioned? Just I'll give an example obviously. Okay, I'll just write here, this one is the beta 1 product topology. Beta 1 is called the product topology. I'll write not beta 1, beta p, beta p for product topology. I'll write beta p for product topology, and this one I'll write beta of b, box topology. Note that for finite situation, this box and product or nothing, these are all same actually. Okay. Okay. So these are rough actually. I will just make this one. Now note that this beta product topology is always contained in beta 2. Always contained, whether I finite or infinite. If finite, then these two are same. But beta p is contained in beta, not beta 2, beta of box topology. How I can show that? For example, let's take 0, 1 is the set, is the xi for all I belongs to the natural number. Okay, this is the set. Consider the product topology. Consider the product topology tau p on product of this particular 0 I is coming from the integer I, right? And box topology tau b on this particular product. Okay, what it means first is that, so here what is the, so if I take an element something like 0, 1, not something like minus 1 by n comma 1 by n, I think, no, sorry, not minus 1 will not work. So better I have to take, this will be, I have to take some little big set. So here what I will take, that minus 1 to 1. Yeah, here I will take minus 1 to 1. Or minus, let's take minus 2 to 2. This is the set. So net what that by basis topology, note that this particular product minus 1 comma 1, this product n belongs to natural number. This is inside the box topology basis, right? That should be just product of all element. Note that here nothing, no, none of the element is same with the set X. None of the element. But this product n belongs to natural number minus 1 by n comma 1 by n does not belongs to the product topology basis. So that means does not belongs to, okay, does not belongs to the basis of the product topology. That means this particular B can be subset of, can be proper subset of BP. Okay, that means there is, sorry, I've written wrong. Product topology basis can be proper subspace of the box topology basis. Okay. Also, similarly, this element obviously not contained in, this element also not contained in the product topology. Note that this product n is coming from the natural number minus 1 by n comma 1 by n is not contained in the topology of product topology. Okay. So box topology is larger than product topology. Here, what is the thing, that how this BP is subset of BB, that implies that product topology is subset of tau of B. BP always subset of product, because whenever elements are finite number of, except finite number of elements are, you can see this set is subset of this set. Clear? There I have added extra condition. Here is no extra condition. So obviously that set is subset of this set, right? So BP, this one is the BP and this is the BB. Is it clear? This product topology and box topology. But why I am saying this product topology and box topology? Because there is some interesting difference we can see in the level of continuous function. On a set, we can give two topology with respect to which the map is not continuous. That already we can give some very easy step. But here what I will say, now one exercise. Let X with tau X be a topological space, and x tau x by topological space. Consider tau p and tau of, consider I is equal to this natural number set, particularly natural number set, and consider product topology on and box topology on this product. I is coming from the natural number set. Here for every I, xi is same. Product topology I denote by, consider product topology ato by tau of p and tau of b respectively, right? Now if I give a map pi, now let's give a map A from x of tau x going to x of tau with the product topology, this product space, and another function g of x going to product of space x, I is coming from natural number, and tau of bx. How this is defined? F of x is equals to x comma x comma x comma all elements are x. How this g is defined? G of x is equals to x comma x comma x comma all elements are like it. Here there is no finite. I am taking I is infinite obviously, so this will go like this. So elements are basically sequence here. Okay. So my claim is that, note, claim is that, note that f and g as a function, note f and g as a function are same. Note f and g as a function. So I can write f and g, not f. F, they are same. Function they are same. Okay. Now claim f from this x tau x to the product xi x, not xi here, x comma tau p is continuous, but if from x tau x to the product of x with the box topology need not be continuous. I am not writing that they will not be continuous, but need not be continuous. Why? First, let's prove first one. Here I will give counter example, and here I will prove this one. Okay. So let's prove first one. How this I will prove that? Any arbitrary open set, any arbitrary basis open set in this product topology xi. Okay, here I will use one fact. I don't know whether I have means very just easy general fact. Let f is a map from x tau x. Now I will not use x here. Y tau 1 tau y1 tau y1 goes to, or just yz, that will be better. Let y tau y goes to z tau z be a map if beta subset of tau z is basis for z tau z, then f is continuous if and only if f inverse of every f set this contains in tau of y for all v belongs to B. What I mean here is that, okay, just I will stop it 1 minute. What I mean here is that, 1 minute, sorry, I will check. One minute, just sorry, 1 minute. Sorry, sorry. Okay. Here, what I want to say here, okay, sorry. Here, what is the f is continuous if and only, okay, that is the thing that for what I am was that f will be continuous. What is the definition? F will be continuous if every open set here, I mean, just for like this, let f is mapped from y tau y goes to z tau z, right? That was the map. Suppose when we'll say that f is continuous, if for every open set here, f inverse of that open set is should be here. That was the thing. But here, what I am saying basically is that okay, we don't need that much bigger thing. What I can say is that if I can show that for every open set, every basis element, every basis element v belongs to b, f inverse v is in tau y, then we will be done. Is it clear now what I want to mean? Okay. If it is not clear, please say it. I will then prove even. I think this is very much easy. If it is not clear, you can ask. I'll prove. This fact I'll use. That's what I'm just trying to say. That I don't need to take f inverse of every element. But if I just take the basis elements, and these basis elements are the open set. I mean, I just supposed to show that f inverse v is open, is in the tau of y for all v belongs to tau of z. Okay, but what I am saying that not for all v belongs to tau z, for all v belongs to the basis b, which is subset of tau z, if f inverse v is in tau of y, still f will be continuous. That is what I am claiming, and that is very much clear. If it is not clear, you can say, okay. If it is clear, say I am not repeating that thing. Basis element, arbitrary basis element in this product topology are something like product of ui such that product of ui such that okay, just product of ui, okay, I'll write it below. Product of ui, I is coming from the natural number set such that the set all I belongs to natural number such that ui is not is equals to xi, here x basically is finite. So that means f inverse of what I just want to say here is that so elements like u1 cross u2 cross up to certain n, it will be in un. Other element obviously it will be other element will be x. Is it clear? At least up to finite number of term. I don't know up to that finite number of term whether all elements will be not x or not. But after that element, every element will be x because finite number of elements can be not x. Okay, finite number of element can't. I mean, not necessarily x, but other element obviously x. So after finite stage, for example, I'm saying that we can think of as a sequence. Okay, what I'm saying that suppose u1 u2 like that way, after a finite stage all element will be necessarily x. Before that we don't know whether they will be x or not. So that means, and whenever element is x, f inverse of x is basically x here because how the function f is defined, that f is something like this way. Okay, so if I take arbitrary basis element like this way, then f inverse of this particular basis element will be product of I will be n, ui will be inverse of f inverse ui, I belongs to natural number such that the set I not is equals to n, I not equals to, sorry, I belongs to n for which u f inverse of ui is not x, not x. This is not x. Uh, this is finite. So what will be like this way? This will be something like u1 product of u2 product of u3 up to some extent it will be un. After that all element will be like x. This will be not product. This will be intersection. Sorry, this will be like intersection of of ui, I is coming from the natural number such that ui is equals to, if I take this set is the finite, this set I will take this and the finite set, this will be like s, then such that s is equals to this one, then no need to write finite, then ui is equals to x for all I belongs to the set x. Okay, so that means it will be basically, I mean after a finite number of term all will be x, and intersection of all those elements, so intersection of ui I is coming from the set s complement, I is not in s, so if I is not in s, then this will be like this is the thing, this is the product actually, but s is finite, sorry, but s is, but complement, but note that complement of s in n is finite, so this is a finite intersection of elements of x, because so and x is topological space, so finite intersection should be again an open set topological space, so then this intersection I belongs to I does not belongs to s, ui is containing x, that means f inverse of this product I belongs to the set natural number ui that is containing x. Is it clear? If it is not clear, then please say it. I will try to discuss. Is it clear? Okay. 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 Yeah. So basically, I have used this one. How it I have used. So instead of taking any arbitrary open set, I have taken a basic open set. How this basic open set is something like this. Arbitrary basic open set is something like this. So now for that arbitrary basic open set, f inverse of this will be something like this particular thing, such that the set S will be finite, such that S here I need to write finite. S is finite. Sorry. This set where UI is not. Sorry. I have missed. But the concept is something like I belongs to S, such that UI not is equals to X is finite. So that means this will be UIX for all I where not I not belongs to X. So then I don't need to X is finite. So this will be like this will be I belongs to S. Okay, if there is any confusion, please say it. I will try to. Basically, what means that except finite number of terms, all term will be X. So those X intersection with those X will not affect anything. So this will be basically intersection of finite number of terms. That is the main thing. And finite intersection of finite number of terms is again in X. But we know that intersection of open set, intersection of infinite number of open set need not be an open set. But if from x tau x to product of x I belongs to natural number subset of the box topology, this box topology need not be continuous. How? Let's take x is equals to -1 to 1 and tau x is standard topology. Okay, standard topology means usual open interval and all those things are the actual open sets. Okay, now if f is something like f is x equals to x comma x comma x comma x. Now okay, now note that -1 by n comma 1 by n product n belongs to natural number is an basic open set in this product topology. Sorry, product topology, not product topology. This is in this what is called box topology. Okay, because in box topology this is not an open set in product topology, because product topology this will be open set if except finite number of terms all terms is the full space. But here you can see that for every n belongs to natural number these are not full set, none of them are full set. Okay, None of them are actually -1 to 1. Oh, sorry, only for n equals to 1. But okay, then I can take uh, just a minute. What you can say is that, now note that 0, I mean, what is the inverse of this particular set? F inverse of product n belongs to natural number minus 1 by n comma 1 by n, which is equals to product n belongs to natural number F inverse of minus 1 by n comma 1 by n, which will be product of n belongs to natural number minus 1 comma 1 by n. But this set is this singleton set. Okay, but this singleton set is not open set in this minus 1 by 1 with standard topology. Okay, is it clear? So F is not continuous. What I have shown that I have taken in I have second what I've shown that I have taken um, an basic open set, okay, and then I have taken inverse of that basic open set and showed that that basic inverse of basic open set is not an open set. So F need not be continuous. So there is a difference that a function can be continuous in some space and but not in other space. And also you can understand the difference between box topology and product topology. Okay. Now what I will say that some properties of I will not discuss those things here. Let F and G from x to y x to y with tau of x going to y with tau of y going to y tau of y are continuous function, are two continuous function, then a plus g is again continuous function, is again a continuous function, is again a continuous function, first property. So particularly if f and j are function from real number to real number, let r square, sorry, r star is equals to r minus 0. Consider subspace topology on this r star. Then if f is a function from this r star going to r star is continuous, then f 1 by f is also a continuous function. 1 by f is continuous function. This is the second. Third is that if f and g are from R to R are continuous function, then f dot g defined from R to R, how this is defined? F dot g at x is equals to f of x, g of x are continuous, is continuous, not this product is continuous. 4, if f and g are from real number to real number are continuous, then f compose g from R to R defined by f compose gx is equals to f of g of x, f of g of xx, again continuous. Okay. Sure. This F composite G is continuous. Fifth is that let F and G from R to R are continuous, then then um, and they are continuous, and G of X is belongs to R star. That means G is not zero basically. For all X belongs to R, then F by G from R to R by F by G X is equals to F of X by G of X is continuous. Okay, this thing. Some example of continuous function is like F from R to R square. Okay, now this is already discussed. R square to R by F of X comma Y is equals to X plus Y is continuous. F from R square to R by F of X Y is equals to X dot Y is continuous. And third, if F from R to R star by giving by R star to by F of X is equals to 1 by X is continuous. Okay. So what I have till now, just these 3-4 things, that if F and G are two continuous function, then their addition will be continuous function, product will be continuous function, composition will be continuous function, and if the function G such that G is not taking value 0, then F by G also be continuous function. And in real line analysis case, that F um, analysis case that like F of F like xy going to x plus y is a continuous function, x comma y going to x dot y is continuous function, and x going to 1 by x is again a continuous function. Okay, is there any problem with this? Is anything what of this particular example or these properties should I prove or discuss here? I mean, if it is needed, if anyone is needed, then I will discuss. Otherwise, I will try to do some other things at least. Is it clear? Five, six, eight things, that F and G are a continuous function, then their addition will be continuous function, and product point to product will be continuous function, composition will be continuous function, and F by G. If there is no problem, then okay, I'll go ahead. If there is any problem, anything that I should prove, then I can prove here. Okay, anything you want to prove here, I'll prove here. Otherwise, I'll do some other problems. Okay, I think no need to prove, right? I think these three, I think Sarah has proved already, and these are also either proved, no, otherwise they'll follow very easily. Except this one by F1, this one will be little trickier. Okay, I will now. I will. Okay, now if anyone is, I mean, not needed, then I'll discuss some problem which will be in which we will use these particular things. Okay, what is that? First of all, very interesting 2-3 problems. First of all, what I want to show here is that let f is a function from r square to r square. How it is defined? F of x comma y is equals to x square plus y square minus 1. Okay, this is the function. You know that x square plus y square is equals to 1 is the equation of circle in r square, right? Now I'm defining fxy is there that way. Now r square and r will have standard topology. Okay, usual standard topology. Okay. Now if I the usual standard topology this x comma y. Now what I want to say is that this function is continuous. First, this f is why this function is continuous. First claim f is continuous. Why it will be continuous? Let's note that x comma y goes to ax. This is projection, and we already proved projection is continuous. Okay. Now suppose this is the projection function. Now take projection dot projection. That means product of projection. When xy goes to x square, this is continuous. Similarly, xy goes to y, this is continuous because projection, and then take product of this function, then that xy goes to y square, this is projection, right? Then addition of these two functions x square plus y square plus addition of the function minus 1, that is constant function, that is continuous. So that means this is this particular expression is actually something like either multiplication or addition or subtraction of continuous function already we have seen. So that means f is continuous. So in that way, whatever we have discussed here, in that way what we can say is that this in that way what we can say that any polynomial function f r to the power n to r, any polynomial function, okay, is continuous. Polynomial function will be something like this. How polynomial function is usually means that suppose x square y goes to all polynomial up to degree less than equals to 2. That means it can contains x square, it can contains y square, it can contains x y, it can contains x, it can contains y, it can contains 1, and any coefficient of them. So this function will be continuous. So like this way, function is continuous. Any polynomial function is continuous. Okay. This is no need of here, but what I want to say is that here what I want to say, this example that f is something, some function is this, then this is continuous, right? So now note u is equals to the set x comma y. Now take x comma y coming from r square such that x square plus y square is equals to 1. Okay, that means we can write this one not equals to 1. So that means this is the set. U is this set. That means this can be written as x comma y belongs to r square such that not u of x, such that f of x comma y is not equals to 0, right? Because this can be written as x square plus y square minus 1 not equals to 0, and that is actually f of x comma y. So what this u set means, the set of all those xy such that f of xy is not equals to 0, right? Now if now note that if I take v is equals to r minus 0, note that function is f from r square to r square. If I take v is r minus 0, then v is open. Why v is open? V means that this full line 0 is except. That means for any element y, I can get an open set containing there, and all those things will be there. So v is open here. Okay. If any doubt, we can ask of this. If why v is open, still I can. V is open, and as f is continuous, f inverse of v will be open in R square, right? Now what is f inverse of v? What is f inverse of v? Clearly f inverse of v will be all those x and y belongs to R square such that f of xy belongs to v. That means all those xy belongs to R square such that f of x comma y which is not equals to 0 because 0 is the only element which is not in V. So if fxy takes value 0, then that will not be V. If it takes any other value, it will be in V. So that means x comma y belongs to R square such that x square plus y square minus 1 is not equals to 1. So this one is open in R square. So what we have proved here basically, this full thing, that this function is continuous, and using the help of this, we have proved that this particular set is open set in R square. Is it clear? Similarly, we can say that space of symmetric matrices and all those things will also be clear. That I will just only prove. Similarly, take MNR be the space of all n by n matrices, just n by n matrices. Okay, and define a function f from MNR to MNR. How it will define? F of A is equals to A transpose minus A, or A minus A transpose. A minus A transpose. I am taking n by n matrix. I can make sense transpose. Okay, there is no problem. Now we know that. By the help of standard topology, of R to the power n square, we can give a standard topology on our MNR that I have discussed in last day. We can give a standard topology on MNR. Okay, so that there will be a standard. So with that standard topology, so with that standard topology, F will be continuous, and if I take similarly the set U is equals to all those A belongs to MNR such that A transpose equals not equals to A is subset of MNR, then U will be open set. That means space of all symmetric matrices are closed. Space of all symmetric matrices in MNR are closed with respect to standard topology. With respect to standard topology of with respect to standard topology of with respect to standard topology of R to the MNR, with respect to standard topology of MNR. Okay, but why it will be open? Because the map F is continuous and the set V is equals to, similarly I can take MNR minus only the zero matrix. Okay, zero element is open in MNR, and inverse image of this particular V is equals to all those A belongs to MNR such that F of A belongs to V, that means all those A belongs to Mn are such that A transpose minus A is not equals to 0. Okay, so that is equals to U. And so if being continuous, F inverse V is open in MNR, that means, is there any doubt? Is there any confusion? Anything I should, I mean, make it clear more or? Okay, if there is any question, please uh, ask here, or I'll stop in 1 minute. If anyone if I don't ask anything, then I'll stop on in 1 minute then. Okay. Okay. So if any don't, I mean, if you don't have any questions, then we can stop here. Okay. Okay. Then we'll stop here.